Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12th physics get more than 95% marks series. Today's chapter is alternating current. Chapter 7 NCERT line by line part 6. Today's lesson will begin with a simple request. Please subscribe our channel if you have not done yet. Please like and share our videos among your friends and relatives, and please click on the bell icon so that you can get automatic notification whenever a new video is uploaded by us and will not miss any of our important videos. Let us begin today's class. Today we'll start with 7.7 section 7.7 power in AC circuit, the power factor. We have seen that a voltage V is equal to Vm sin omega t applied to a series RLC circuit derives a current in the circuit given by Im is equal to Im sin omega t plus phi, where Im is equal to Vm upon Z and phi is equal to tan inverse Xc minus XL upon R. This we have already studied and we know how to derive in the last classes, in the previous classes. Therefore, the instantaneous power supplied by the source is, we know, P is equal to V into I, potential difference into current. Power is equal to potential difference into current. So put the value of V from here and I from here. So this is V and this is I. So upon simplifying, we get this value. This is written as equation 7.37. Now the this value can easily come by the trigonometric formulas. So just implement the trigonometric formula, it will automatically it will give this value. Now the average power over a cycle is given by the average of two terms in RHS of equation 7.37. It is only the second term which is time dependent. Why? Because the second term contains time. Here 2 omega t. So time t is there. So second term is time dependent. Its average is 0. The positive half of cosine cancels the negative half. Therefore, we can write P is equal to Vmim upon 2 into cos phi. So this whole term becomes 0. The second term becomes 0. So we can write the same as Vm upon root 2 multiplied by Im upon root 2 cos phi. So we have written 2 as root 2 multiplied by root 2 and we have put this 2 separately. So why we have done that? To write this we will write as V and this whole will write as I. Not this whole, this one will write as I and this one will write as this. So V into I into cos phi. So this is equation 7.38a. This can also be written as P is equal to I square Z cos phi. So this the same can be written as. So we can write V as I into Z. So it will be written as P is equal to I square Z cos phi. So the average power dissipated depends not only on the voltage and current, also on the cosine of the phase angle phi between them. The quantity cos phi is called power factor. Let us discuss the following case. Case 1, resistive circuit. So if the circuit contains only pure R, it is called resistive. In that case, phi is equal to 0, cos phi is equal to 1. There is maximum power dissipation. Case 2, purely inductive or capacitive circuit. If the circuit contains only inductor or capacitor, we know the phase difference between the voltage and current is pi by 2. We have done this concept in our previous lessons. Therefore, cos phi is equal to 0 and no power is dissipated even though the current is flowing in the circuit. This current is sometimes referred as wattless current. So one more question can be asked, what is a wattless current? So they can give a scenario and they can ask uh, what will be the current flowing in the circuit, and in this way they can ask many questions. So if your concepts are clear, then any and every question can be answered. Case 3, LCR series circuit. In LCR series circuit, power dissipated is given by equation 7.38. 7.38, let us see 7.38. So these are 7.38. This is the, so 7.38a, 7.38b. So where phi is tan inverse xc minus xl upon r, and so phi may be non-zero in RL or RC or RCL circuit. Even in such case, power is dissipated only in the resistor. Case 4, power dissipated at resonance. In LCR circuit, at resonance, xc minus xl is equal to 0, phi is equal to 0. Therefore, cos phi is equal to 1. So cos phi is equal to 1. Therefore, cos phi is equal to 1. P is equal to I square Z is equal to I square R. That is maximum power dissipated in the circuit through R at resonance. And these are the 4 cases. So let us see few of the numericals example. So example 7.7a, for a circuit used for transporting electric power, a low power factor implies large power loss in transmission. Explain. B. Power factor can often be improved by using capacitor of appropriate capacitance in the circuit. Explain. So we know that first part A, we know that P is equal to IV cos phi, where cos phi is the power factor. To supply a given power at a given voltage, if cos phi is small, we have to increase the current accordingly. But this will lead to a large power loss, I square R, in transmission. So if cos phi is less, then we have to increase the current I. But this will lead to a great loss by Joule's theory, I square RT, uh, I square R in the transformation. Okay. Now B part. Suppose in a circuit the current I lags the voltage by angle phi, then power factor cos phi is equal to R upon Z. we can improve the power factor leading to 1 by making Z tends to R. Let us understand with the help of phasor diagram figure 7.17 how this can be achieved. Let us resolve I in two components IP along the applied voltage V and IQ perpendicular to the applied voltage. So here is I, which makes an angle phi with V. So I is resolved into two components. One is I, IQ and another is IP. IP is along V, the voltage, and IQ is along perpendicular to IP or the voltage. Then IQ, as you have learned in section 7.7, is called wattless component. Wattless component. Since the since corresponding to its component is current. Uh, so it is wattless. Therefore, no power loss in IP. So IP is known as the power component because it is in the phase with the voltage and correspond to the power loss in the circuit. So this is the for this component IP there is no power loss. Only the power loss is due to IP and because it is lying with the voltage. It's clear from the this analysis that if we want to improve power factor, we must completely neutralize the lagging wattless current IQ by an equal leading wattless current IQ dash I dash Q. This can be done by connecting a capacitor to appropriate value in parallel to IQ and I dash Q. Cancel each other and P is effectively IPV. Example 7.8. A sinusoidal voltage of peak value 283 volt and frequency 50 Hz is applied to a series LCR circuit in which R is equal to 3 ohm, L is equal to 25.48 mH, C is equal to 796 mu F. Find A. The impedance of the circuit. B. The phase difference between the voltage across the source and current. C. The power dissipated in the circuit. And D. The power factor. So, to find out the impedance of the circuit, we first calculate XL and XC. So, XL is equal to 2 pi nu L, that is, put the value of pi, nu, the frequency, and L, we get 8 ohm. Xc 1 upon 2 pi nu c. So put the values of pi, nu and c, and so we get Xc is as 4 ohm. Now impedance Z is equal to under root R square plus XL minus XC whole square. Put the value of R, XL and XC which we have derived previously, and we get the value of impedance, that is Z is equal to 5 ohm. The phase difference phi is equal to 10 inverse XC minus XL upon R. Put the value of XC, XL and R, we get 10 inverse uh, inverse value, and it is minus 53.1 degree. Since phi is negative, the current in the circuit lags the voltage across the source. So C part, the power dissipated by the circuit is P is equal to I square R. Now I is equal to Im upon root 2. Then put the value of Im, and it is 40 ampere. Therefore P is equal to 40 square plus put the value of I square, which we got 40, and R, put the value and we get 4800 watt. Power factor cos phi is equal to cos, give the value of phi, which is 53.1. We get power factor's value, that is 0.6. Now let us see the question number 7.9. Suppose the frequency of the source in the previous example can be varied. A. What is the frequency of the source at which resonance occurs? B. Calculate the impedance, the current, the power dissipated at the resonant condition. Solution. The frequency at which the resonance occurs is omega naught is equal to 1 by under root LC. Put the value of L and C, you get this much, omega naught is equal to this much. VR is equal to omega naught upon 2 pi. We get, this is not V, this is nu. This is the frequency nu. So 35.4 hertz. How we got this value? We know that omega is equal to 2 pi nu. So nu is equal to omega naught by 2 pi. So the same formula is used here. The impedance Z at resonance condition is equal to the resistance, that is Z is equal to R, which is equal to 3 ohm. The RMS current at resonance is equal to V by R. So how to remember? V is equal to IR. IR. So I is equal to V by R. In case of resistance it is this, and in case of impedance we can write V by Z. I is equal to V by Z. Similarly, we have written here. So, which is equal to V by R, put the values, you get the value of I. The power dissipated by the resonance at resonance is P is equal to I square R, put the values and you get the power. You can see that in the present case, power dissipated at the resonance is more than the power dissipated in example 7.8. So let us see the next sum. Example 7.10. At an airport, a person is made to walk through the doorway of a metal detector for security reasons. If she or he is carrying anything made of metal, the metal detector emits a sound. On what principle does the detector work? The metal detector works on the principle of resonance. This is very important in AC circuit. When you walk through a metal detector, you are in fact walking through a coil of many turns. The coil is connected to a capacitor turned on a turn so that the circuit is in resonance. For you to walk through the metal in your pocket, the impedance of the circuit changes, resulting in significant change in current in the circuit. This change in current is detected and the electronic cir circulatory causes a sound to be emitted as an alarm. So this is one of the important questions. So please go through it. Now we'll start with LC oscillators. So 7.8 LC oscillator. We know that a capacitor and an inductor can store electrical and magnetic energy respectively. When a capacitor, initially charged, is connected to an inductor, the charge on the capacitor and the current in the circuit exhibits the phenomena of electrical oscillation, similar to the oscillation in the mechanical system. Let capacitor be charged Qm at t is equal to 0, means initially it is charged as Qm, and connected to a inductor as shown in figure 7.18 in this figure. So at the instant shown, the current is increased, so the polarity of the induced EMF is in the inductor is as shown. So here this is capacitor, this is the inductor. So this is A is plus, B is minus, this is the current flowing, that is induced current, that is I. Let Qm is the charge of the capacitor at t is equal to 0. The moment the circuit is completed, the charge on the capacitor started decreasing, giving rise the current in the circuit. Let Q and I be the charge and current in the circuit at time t. Since di by dt is positive, the induced EMF in L will have polarity as shown, that is VB is less than VA. So the polarity, the potential difference VB is less than VA. Why? Since di by dt is positive. So the potential difference of VB is less than BA. According to the Kirchhoff's rule, we can write Q upon C minus L dt upon di by dt is equal to 0. So so by Kirchhoff's law, Q upon C minus L di by dt is equal to 0. This is 7.39. I is equal to minus dq by dt. In the present case, Q is decreasing, I is increasing. Therefore, equation 7.39 becomes d2q upon dt square plus 1 by Lc Q is equal to 0. So uh, we have differentiated this equation and we got this value. The equation has the form d2x upon dt square plus omega naught square x plus 0. Now we can write for a simple harmonic oscillator. The charge therefore oscillates with a natural frequency omega naught is equal to 1 upon under root Lc. This also we have done in our previous classes, and varies sinusoidally with time as q is equal to qm cos omega t plus phi. This is equation 7.42, where qm is the maximum value of q and phi is the phase constant. Since q is equal to qm at t is equal to 0, we have cos phi is equal to 1 and phi is equal to 0. Therefore, in the present case, q is equal to qm cos omega naught t. This is equation 7.43. Current I is equal to minus dq by dt. Then we can write I is equal to Im sine omega naught t, where Im is equal to omega naught qm. So what we have done, we have just differentiated uh, with respect to t. So dq by dt we can write. So after differentiation, we get, if we differentiate this equation, then dq by dt is equal to qm minus cos omega t. So cos omega t's differentiation is minus sine omega t, and minus sine omega t we can write I. So we can write it as minus sine bracket minus sine omega naught t, and omega naught t's differentiation is omega naught. So ultimately we can write q by dt is equal to I, q by dt is equal to I. So if we multiply both sides by minus, then minus dq by dt is equal to y here, and minus minus gets plus. So qm omega naught sine omega naught t. So qm by omega naught, we can write this as Im. So ultimately the equation becomes I is equal to Im sine omega naught t. This is the equation, and we have written this equation here. I is equal to Im sine omega naught t, where Im is equal to omega naught qm. Let us now try to visualize how the oscillation takes place in the circuit. Figure 7.19a. So let us see this figure. These are 7.19. Shows a capacitor with initial charge Qm connected to an ideal inductor. The electrical energy stored in the charged capacitor is UE is equal to half Qm square by C. Since there is no current in the circuit, energy in the inductor is zero. Thus, the total energy of LC circuit is U is equal to UE is equal to half Qm square by C. So this is the total energy of LC circuit. Now, the oxidation of LC circuit and analogues of the oscillations of the block at the end of the spring, the figure dissipates one half of a cycle. So let us move forward. At t is equal to 0, the switch is closed and the capacitor starts to discharge 7.19b. As the current increases, it sets up magnetic field in the inductor, and thereby some energy gets stored in the inductor in the form of magnetic energy. So UB is equal to half Li square. As the current reaches its maximum value Im at t is equal to t by 4, as in figure 7.19c. So B's value is, so B's value they have indicated in this way. As the current increases, it set up a magnetic field in the inductor, and thereby some energy is stored in the inductor in the form of magnetic energy. UB is equal to half Li square. So this is the case, and in the at as the current reaches its maximum value Im at t is equal to t by 4 in figure 7.19, all the energies are stored in the magnetic field. UB is equal to half Li square m. You can easily check that the maximum electrical energy equal to the maximum magnetic energy. The capacitor now has no charge and hence no energy. The current now starts charging the capacitor. In figure 7.19d, the process continues till the capacitor is fully charged at t is equal to t by 2, figure 7.19e, but it is charged with a polarity opposite to the initial state in 7.19a. The whole process just described how now repeat itself till the system reverses its original state. Thus, the energy in the system oscillates between the capacitor and inductor. So, this is an example given with the help of graph. They have explained the thing. The Lc oscillation is similar to the mechanical oscillation of a block attached to a spring. The lower part of each figure 7.19 depicts the corresponding stages of mechanical system. A block attached to the spring, as noted earlier, for a block of mass m oscillating with a frequency omega naught, the equation is d2x upon dt square plus omega naught square x is equal to 0. Here omega naught is equal to under root k by m, and k is the spring constant. So x corresponds to q, x corresponds to q. In case of mechanical system, F is equal to ma, m and a we can write dv by dt. Again we can write m d2x upon dt square. For an electrical system, E is equal to minus L di by dt is equal to minus L d2q by dt square. Comparing these two equations, we can see that L is the analogous of mass m. M is the a measure of resistance change in circuit. In case LC circuit, omega naught is equal to 1 upon under root LC, and mass of the spring omega naught is equal to under root k by m. So 1 by c is the analog of k. The constant k is equal to F upon x tells us the external force required to produce an unit displacement, whereas 1 upon c is equal to V by q tells the potential difference required to store the unit charge. Table 7.1 gives the analogy between the mechanical and electrical quantities. Now let us go through the table so that we can understand better. So in mechanical system, whatever if whatever the mass meant by in mechanical system, the same thing is meant by L, inductance. Mass is equivalent to inductance in the electrical system. Force constant K is reciprocal capacitance. It is equivalent to reciprocal capacitance, that is 1 by C in electrical system. Displacement x is equal to charge q. Velocity v is equal to dx by dt. Current I is equal to dq by dt. Mechanical energy is equal to electromagnetic energy, and the mechanical energy is equal to half kx square plus half mv square. Here U is equal to half q square by c plus half Li square. So this is the analogies between the mechanical and electrical quantities. Note that the above discussion of LC oscillations is not realistic for two reasons. First, every inductor has some resistance. The effect of resistance is to introduce a damping effect on the charge, and the current in the circuit, and the oscillation finally die away. Even if the resonance were zero, the total energy of the system would not remain constant. It is radiated away from the system in the form of electromagnetic waves discussed in next chapter. In fact, radio and TV transmitters depends upon radiation. So here two different phenomena in same mathematical treatment: forced oscillation and driven LCR circuit. So equation here in the first part is m d2x upon dt square plus b dx by dt plus kx is equal to f cos omega dt. Similar equation can be written in LCR circuit L d2 q by dt square plus r dq by dt plus q by c is equal to Vm sine omega t. Displacement x can be written as charge on the capacitor q. Time is time in both this in both the process. The mass m is can be represented as self-inductance L, damping constant B is equal to resistance R, spring constant K is equal to inverse of capacitance 1 upon C, driving frequency omega D is equal to driving frequency omega, natural frequency of oscillation omega, natural frequency of LCR circuit is equal to omega naught. Amplitude forced amplitude of forced oscillation A, maximum charge stored is Qm. Amplitude of driving force F naught, amplitude of applied voltage Vm. So these are the physical quantities which can be written as equivalent to the mechanical physical quantities. Okay, let us do few of the sums. Example 7.11. So that in a free oscillations of an LC circuit, the sum of the energies stored in the capacitor and the inductor is constant in time. Solution: let Q naught be the initial charge on the capacitor. Let the charged capacitor be connected to the inductor of inductance L. As you have studied in section 7.8, the LC circuit will sustain as oscillation with the frequency. So omega is equal to 2 pi nu, and which is again equal to 1 by under root LC. At the at an instant t, charge q on the capacitor and the current I is given by q uh, is equal to q naught cos omega t, I is equal to minus q omega sin omega t. So energy stored in the capacitor at time t is equal to ue is equal to half cv square is equal to half q square by c is equal to we can put the value of q, we'll get q naught square upon 2c, that is cos omega t. So energy stored in the inductor at time t is equal to is equal to half L t square, half L uh, q naught q naught square omega naught square sine square uh, q naught square omega square sine square omega t. So just just put omega square is equal to 1 by L under root LC, if and simplifying we get this value q naught square by 2c sine square omega t. Sum the energies, so ue plus is equal to q naught square upon 2c cos square omega t plus sine square omega t. So cos square omega t plus sine square omega t is equal to 1. So q naught square upon 2c. The sum of is constant. The sum is constant in time as q naught and c both are time independent. Note that it is equal to the initial energy of the capacitor. Why it is so? Think. Now we'll start with the next topic, that is transformers. So transformers. For many purpose, it is necessary to change or transform an alternating voltage from one to another or greater to smaller value. This is done with the device called transformer. So what a transformer? It transforms or changes the voltage from one to another or greater to smaller. That is transformer using the principle of mutual induction. So on what principle transformer works? It works under the principle of mutual induction. A transformer consists of two sets of coil insulated from each other. They are wounded on a soft iron core, each one on top of the other as in the figure 7.20a, or separate limbs of core as in 7.20b. So let us see 7.20a and b. So two arrangements of winding the primary and secondary coil in transformer. First, A, the two coils top of each other. B, the two coils separate limbs of core. So in this case, this is primary, this is secondary. In this case, this is primary, this is secondary. Now, one of the coil is called primary coil, has a NP turns. The other coil is called secondary coil. It has NS turns. Often, the primary coil is the input coil and secondary coil is the output coil. So, primary coil is the input coil, remember, and secondary coil is the output coil of the transformer. When an alternating voltage is applied to the primary, the resulting current produced an alternating magnetic flux which linked to the secondary and induces an EMF in it. The value of EMF depends on the number of turns in the secondary coil. It considers an ideal transformer in which the primary has negligible resistance and all the flux in the core links both primary and secondary windings, and phi is the flux in each turn in the core at time t due to the current in the primary when a voltage Vp is applied to it. Then the induced EMF or voltage Es in the secondary with turn ns with ns turn is Es is equal to ns d phi by dt. This is 7.45. The alternating flux phi also induces an EMF called back EMF in the primary. This is EP is equal to minus NP d phi by dt. This is equation 7.46. But EP is equal to Vp. If this were not so, the primary current would be infinite since the primary has zero resistance as assumed. If the secondary is an open circuit or the current taken from it is small, then to a good approximation Es is equal to Vs, where Vs is the voltage across the secondary. Therefore, equation 7.45 and 7.46 can be written as Vs is equal to Ns d phi by dt. Vp is equal to minus Np d phi by dt. So this is equation 7.46a, and this is equation 7.45a. From the equation 45a, 7.45a and 7.46a, we can write Vs by Vp is equal to Ns by Np. If we divide this two equation, then this will get cancelled. d phi by dt is will get cancelled, and we get Ns upon Np, and in left hand side we get Vs upon Vp. So note that the above relation has been obtained using the three assumptions. First, the primary resistance of the circuit is R small. B, second, the same flux length, both the primary and secondary are very little flux escapes from the core, and third, the secondary current is small. If the transformer is assumed to be 100% efficient, no energy loss, the power input is equal to the power output, and since P is equal to IV, we can write IP Vp is equal to Is Vs. So this is one more condition. This can be represented as 7.48 V. 7.48. Although some energies is always lost, this is a good approximation since a well-designed transformer may have an efficiency more than 95%. Combining equation 7.47 and 7.48, we get Lp upon Ip upon Is is equal to Vs upon Vp is equal to Ns upon Np. Since I and V both are both oscillates with the same frequency as the AC source, equation 7.49 also gives the ratio of the amplitude of RMS value of the corresponding quantity. Now we can see how a transformer affects the voltage and current. We have Vs is equal to Ns upon Np multiplied by Vp, and we have Is is equal to Np upon Ns multiplied by Ip. This is equation number 7.50. That is, if the secondary coil has a greater number of turns than the primary coil, that is Ns is greater than Np, the voltage is step up, that is Vs is greater than Vi. This type of arrangement is called step up transformer. However, in this arrangement, there is less current in the secondary than in the primary. Np upon Ns is less than 1, and Ns is less than Is is less than Ip. So these are the conditions you have to remember for a step up transformer. For example, if the primary coil of a transformer has 100 turns and the secondary coil is 200 turns, Ns by Np is equal to 2, Np by Ns is equal to half. Thus, 220-volt input and 10 ampere will step up to uh, 2 2 into 220, that is 440 volt. This one output as zero point 0.5 ampere. So output as 5 ampere. Why 10 ampere? Divide by 2, I is divided I half I by 2, so it is 5 ampere. If the secondary coil is less turn and then the primary coil, that is Ns is less than Np, we have step down transformer. In this case, Vs is less than Vp and Is is greater than Ip. That is the voltage in step down or reduced, and the current increases. The equation obtained above apply the ideal transformer without any energy loss, but the actual transformer some energy loss lose due So, some small energy losses do occur due to the following reason. Flux leakage. There is always some flux leakage. That is, not all the flux due to the primary passes through the secondary due to a poor design of the core or air gaps in the core. It can be reduces by winding and the primary and secondary coil one over the other. Second, resistance of the winding. The wire used in the winding has some resistance and so energy loss due to heat produced in the wire I square R. In high current, the low voltage windings, are many. There are These are maximized by using thick wires. Next is eddy current. The alternate magnetic flux induced eddy currents in the iron core and cause heating. The effect is reduced by having terminated core. Hysteresis, the magnetization of the core repeatedly reversed by the alternating magnetic field. The resulting expenditure of the energy in the core appears as heat and is kept minimum by using a magnetic metal which is a low hysteresis loss. The large-scale transmission and distribution of electrical power energy over a long distance is done by the use of transformer. The voltage output of the transformer is stepped up, so the current reduced and consequently with I square R loss is cut down. In that it is then transmitted over a long distance to an area substation near the consumer. There the voltage is stepped down. In It is further stepped down at distributing substations and utility poles before the power is supplied to 240 volt reaches to our home. So this is the end of this chapter. Before we close today's class, we request you to subscribe our channel if you have not done yet. Please like our videos and share among your friends and relatives so that this channel can grow with your help. Please click on the bell notification so that you can get automatic notification whenever a new video is uploaded by us, and you should not miss any of the important videos. Thank you very much for watching our videos and supporting us. Thank you.